In this video we're going to calculate enzyme activity. This is something which often causes students problems, and it's normally because they have failed to keep track of the units. So let's just remind ourselves what enzyme activity is. It's the ability to produce product in a certain amount of time. So the normal unit of enzyme activity is micromoles of product formed per minute. So often that's called 1 unit of enzyme activity, the ability to produce 1 micromole of product in 1 minute. Now let's suppose that we do an assay, and let's suppose there's a colorimetric assay. So we've got a cuvette over here, and in this cuvette we've got 980 microliters of substrate, and to that we're going to add 20 microliters of enzyme. And we're going to incubate for 5 minutes. And after that 5 minutes, we're going to stop the reaction somehow, and it's quite common to stop the reaction of an enzyme solution by adding it to a buffer which has got a much higher or much lower pH. So let's say that after 5 minutes, we take this 1 ml, 1000 microliters of solution, and add it to 3 mils of a buffer, say it's at pH 10. Okay, so this is 4 mils in total. So we've got 1 mil coming from here, we're adding it to 3 mils. So that means in here, we've got 4 mils in total. So let's imagine that we take that 4 mils and we measure the absorbance of it in a spectrophotometer, and let's say that the absorbance there, A, is equal to 0.35. So the absorbance of this here is 0.35. Now, that absorbance change has been caused by the enzyme converting substrate into product in 5 minutes. So the change in absorbance, so we can say delta A, the change in absorbance per minute, is equal to 0.35 divided by 5 minutes. Absorbance have got no units there, so that there is equal to 0.07 per minute. So we have an absorbance change of 0.07 per minute being produced there. Now that's an absorbance change. We want to convert that into concentration, so we need the Lambert Law. So Lambert Law says that A is equal to ECL, so C, the concentration there, is equal to the absorbance divided by the absorption coefficient times the path length there, which is going to be equal to 0.07 per minute here, divided by, well, if this was beta-galactosidase, the enzyme was beta-galactosidase, and the substrate was ONPG, so we'll say that here that the absorbance coefficient here is 4600, and that's liters, moles to the -1, centimeters to the -1 there, and that's multiplied by the path length here. Let's say the path length was 1 centimeter there. So the concentration change after 5 minutes there was, this out, is 1.52, and the centimeters cancel out there. The liters becomes per liter, the moles become, moles to the -1 become moles there. So the answer here is 1.52 times 10 to the -5 moles per liter per minute. So this amount of enzyme here, this 20 microliters of enzyme, manages to produce 1.52 times 10 to the -5 moles per liter per minute. Putting that into other units, that would be 15.2 micromoles per liter per minute. What I've done there is I multiplied that by 1,000,000 to get moles into micromoles there. and that was produced by 20 microliters of enzyme there. We don't want micromoles per litre per minute, we want micromoles per minute, so we need to get rid of this litres somehow. So we need to multiply this, that's the concentration there. So the absolute amount of moles is going to be equal to, so this is going to be moles, or rather micromoles per minute, is going to be equal to 15.2 micromoles per litre per minute, multiplied by the number of litres. Now the number of litres here is 4 mils divided by 1,000 mils there, so that number of litres there, which is equal to 0.0609 micromoles per minute. So this amount of enzyme has produced 0.0609 micromoles per minute, or 0.0609 enzyme units there. That was 20 microliters of enzyme. So that's not a terribly useful amount. That's not an amount we'd normally think about. Normally we'd think about mils of enzyme might be a more useful figure to put that into. So this there was 0.0609 micromoles per minute per 20 microliters of enzyme there. So if we had 1 mil there, then that would be 0.0609 multiplied by 1,000 microliters divided by 20 microliters, that number of mils there, which is equal to 3.04 micromoles of product formed per minute per mil of enzyme. So it's kind of like a 3-step calculation is what we're doing here. We're figuring out what the absorbance is in here. We're converting that absorbance into a concentration. We're then converting that concentration into an absolute number of moles of product formed per minute. And we're then saying, well, that was for 20 microliters of enzyme. If we'd used 1 mil of enzyme, we would have got that number of enzyme units. So we've just calculated the number of enzyme units that this enzyme solution here has got per mil. So in other words, you take a mil of that solution that contains that enzyme and we can get 3.04 micromoles of product being formed per minute. Now that's all very well, but often we want to know the specific activity. Now the specific activity is a measure of purity of the enzyme. This value here, this mil value, doesn't tell us anything about how pure that enzyme is. Now what we mean by pure is how much of the active enzyme is there compared to all the other proteins that might be in this solution that we've been using here. So what we can do is we can take this figure here per mil, and instead of expressing it per mil of enzyme solution, we express it per milligram of protein that's in that solution. So let's imagine that this enzyme solution that we've been using has got a protein concentration of 10 milligrams per mil. So we do another assay on this solution and we find out that for every milliliter of it there's 10 milligrams of protein there. Well, the specific activity of that solution is going to be equal to the activity here, 3.04 micromoles per minute per mil, divided by 10 milligrams per mil here. And so the answer to that is 0.304 micromoles per minute. Well, those mils cancel out there. We're left with these milligrams here per milligram. So if we had this many units per mil, units of enzyme activity per mil, and we knew that that solution, that enzyme solution, had a protein concentration of 10 milligrams per mil, the specific activity of the solution is equal to 0.304 micromoles per minute per milligram of protein. And that's a really useful figure because it tells us something about how pure that protein solution is.